Hey, Colton, good to see you here. Who else do we have in the chat? We got Mubot in the chat, so let's give out some points. With that, Colton's asking about BAS 475, question 3 for this week's homework. Let's put on a little music right here, and let's start it up. Yes, that's a good question right there. Colton, how are you doing today? We're going to go take a look at this question, find out what it is. If you're here for 201, we've got the exam on Wednesday. So let me know what you're working on. Start working on the exam Wednesday. Decomposition assignment. Ooh, decomp. What is decomposition? It's breaking down a time series component, or breaking down a time series into its components, decomposing it. So with that, clear off some of my data sets right here. Take a look. Question 3. Okay, got the Box Cox transformation. Okay, let's get ready here. Take some notes. If you're in the chat, say hey. We've got here 205, BAS 475, assignment 4, question 3, Box Cox. And the time is now on the 18-second mark. Let's go check it out. Here we go. Okay, so what is the Box Cox transformation? So the Box Cox transformation is basically a series of transformations. And what do we mean transforming data? So Colton, what does it mean to transform data? Transforming data is the first thing we really need to understand. So let's take some notes right here and say, what is transforming data? So we might have a data set that looks something like this. R exponential, and let's take 1,000 data points right here. Don't worry about that. We're just going to call it X. And here's our data set. Now, that's just the values. Those are a bunch of, like, maybe people said, how many minutes to complete a task? Simplify. I'll go with that. I like that answer. Kind of re-expressing patterns. Like, data has information in it, and maybe there's a different way to express it. Like, to transform it would mean, imagine this. A usual transformation that we use, a very common transformation, is going to be something like log transformations. And the reason we use log transformations, which you'll see here in a second, is if you have a vector, something like 1, 10, 100, 1000, this is actually a very, so let's just call this vector. And the vector, when you view it in a histogram, is going to have a lot of separation between the points. It's mad about my window size right there, so a little more. There we go. Let's add in some breaks to this. Oh, I added 2 100s. I wanted 1,000. Breaks equals, let's go to 10, and let's put in a 10,000. And there we go right there. So this is a very, very right skew histogram, and because 1, 10, 100 are in this bin right here, and then 1,000's in this bin over here. So with this, we could re-express this data and transform it to something that's more normal. And the reason we try to go towards normality is because then we kind of get an idea of spread of values. Right now, everything's kind of clumped up in this one area. So if we re-express it, things might have more of standardized metrics of distances, and then it would make more sense to say how far something is from something else. Good evening, Brianna, or good afternoon. Ask any questions you got. We're doing some 475, then we can do 201, 320, whatever you like. And so what we do right here is we have right now a histogram of X, which is also very right skew. This is an exponential function creating it. So you'd see here very extreme values. So we could re-express it by going here to log 10 of it. We can log by any value, and there's the log 10 values, but we could view it as a histogram now, and you'll see it looks a lot more normal. Now, it's not perfectly normal, but this is via transformation. So all these values here are transformed. It's important to understand that logs pull in extreme values. That's a very important key thing to remember, that when you log something like this vector right here, where the vector is 1, 10, 100, 1000, using the log 10 brings it down to 0, 1, 2, 3. And we can see this. We should know a little bit of math to know how that's done, but the log question asks, what power do we raise the base of 10 to get 1? You'd have to raise 10 to 0. 10 to 0 is 1. What power do you raise 10 to get 10? You raise it to 1. What power do you raise 10 to get 100? You raise it to 2. Logs are oftentimes a little bit confusing, but it goes by the question of what power do you raise the base to obtain the number in the original vector? And so you can see right here, I used values that go in order 0, 1, 2, 3. Sometimes your values are not that pretty, though. They might be something like this. And so you might get values right here, but you can kind of estimate from this that this is going to be 0, 1 something, and 3 something. So 0, 1, 3, 3, and there it is right there. But once again, I'm just doing estimates, but I do know what logs do. It's not important to solve logs in your head. It's important to understand that logging a vector pulls in extreme values. And we can see this here visually, that when we have an extreme value of distribution, or extreme values, what do I mean by extreme values? Extreme right skew. There's very high values that are far away from the centrality of the data. Then we can go right here and we can pull in those extreme values and get a more normalized distribution. Now, when you think about the standard normal curve, which applies to 201, the goal of the standard normal curve is to turn things into z-scores. So we could take this afterwards and scale it, something we saw originally, and now we can see right here they are z-scores, which scaling something, I do want to point this out, scaling does not transform the data in terms of changing the shape of the distribution. It does standardize the values. That's what scaling does. Let's put a key note right here. Logging or scaling does not transform values. It standardizes them, i.e. turns them into z-scores, which is a form of standardization. And then we have right here, logging does transform data. So where does this brings us back full circle to what is the Box Cox transformation? So the Box Cox transformation is a series of different lambda values, and we could go look at this. I'm going to bring up the book right here, that try kind of what we call a family of transformations. Like we're auditioning different different transformations right here to kind of move the data into a different shape. So let's take a look at this. I'm going to bring up the book because there's really good examples. I might bring up the applet we created for it. So transformations and adjustments, and here we go. Does he have the... Oh, he does. Good, good, good. He has it in here. Here it is right here. So this is what we're talking about when we talk about the Box Cox transformation and this value of lambda right here. So this value of lambda is like what we are using, say, transform with a lambda value of this. Now, there's infinite values of lambda because you will not solve the equation. The equation, I think he shows up here. We'll slide. Here's the way the equation works. And you notice right here, log, if it's 0, so it does do the log in the possible values. Then it does the sign, all this good stuff right here. We do not solve this. But once again, the transformation is based on the value of lambda, and only in the one instance when lambda is set to 0 does it try the log of the vector. I believe that's natural log right there. Wouldn't GDP per capita be a transformation? That's kind of a creation variable. So it is transforming to a certain extent. But that would be like a variable creation, which is a transformation of sorts. So it basically just changes the scale of the graph. Like when you do GDP per capita, that's going to create a new variable. But when we talk about it here, is we're going to like do it. So if you notice, like in your example right there, you have like GDP, and then you're saying per capita, which that will not change the shape of the distribution because per capita is going to be a constant metric. What's different about these, and Colton, great answers right here. What's different about these is that it's not a constant metric on this. Does that make sense? Like the transformation to this data right here, unless you do it like where countries have different GDPs and different per capita or different per capitas, the transformations will change the what of the distribution, which this goes to 201. A transformation will change the what of a distribution. This is a 201 question. So a transformation will change the what of a distribution. This literally goes back to 201. I try to tell everyone that everything we talk about goes back to 201. A transformation will change the what of a distribution. So histograms have the first feature we talk about, and you are seeing it change when we do a transformation. The shape, exactly, Colton. Yep. So if it does change the shape, it has transformed the distribution. So if you do a GDP per capita calculation and it changes the shape, which like log transformations do, then you've achieved a transformation. You could re-express something, but scaling, which GDP per capita sounds more like a scaling to me, like bringing it down to like a per million or per thousand or something like that. That won't change the shape of the distribution. So we have to make sure when we talk about a transformation right here, it's going to change the shape. And you can see this in the time series below right here. What we're trying to actually obtain is, interestingly enough, what do you think is something good? And this goes to tool 1 also. Where do you think the optimum value of lambda is? And what do you think we might try to obtain in this time series right here, which maybe the optimum value of lambda is over here? This literally goes to chapter 6, because I'll tell you this much, that is not an optimum value of lambda. The optimum value of lambda might be in here somewhere. And I'm looking for a pattern that kind of goes like this. What do you think I'm trying to achieve right here, Colton, with the optimum value of lambda, which we don't have to find. It'll be found for us. But once again, we can try many different values of lambda. Does it say works quite well? 0.1 they're suggesting. Let me go to their thing, go to 0.1. Sure, that's what they're saying they like. I don't know. I kind of like that. I don't know. I'd love to see the time series worked out. I can tell you definitely it's not this down here, and definitely it's not this over here. It's somewhere in a range down here. Like they're saying that. I like over there probably. We can disagree. The book and I can disagree. He wrote the book, but I can disagree with him still. I can always disagree. So let's try a lambda. There's a lambda 0.12. Is that the one that was found? Oh. So what we're doing right here is we're trying different values and different ways to transform the distribution. And what do you think is something good to achieve with the way the distribution looks? We probably want it to look mostly what, Colton, which is a 201 topic, chapter 6. We probably want to achieve something that looks mostly, and I'll drop you some hints right here, with this transformation. And to talk about the series right here, there's a few things to talk about. One, it'd be great if we could get that, and 2, and that's probably what they're going for, it'd be great if we could get this. So this transformation has achieved a lot of good goals right here. Linear, Brianna right there. Yep, linearity. We'd like something mostly linear. It is a little bit S-shaped, right? So it's not quite a logistic regression or something. We're not going to do a logistic. I guess we could fit a logistic curve to it, because you can always fit different equations to stuff. But we do like to achieve linearity with our time series. And also the yellow bands are what? So Brianna and Colton, great work, and I'm still on top chat. But the yellow bands suggest to us that we might have achieved some sort of a plot not thickening issue, which we call what? So Brianna, I think you're in 201. You will hear this later on. We don't want the plot to get thicker or thinner. We want it to have the same relative thickness throughout. I guess if you do, there's other ways to handle it. But this is, yeah, I guess he's right. That's got about the same relative thickness throughout. So what do we call that, Colton? I'll give it a second right here, but this is a really good review of stuff, and then we'll go ahead and solve the question. But we want to achieve mostly linear, mostly homoscedastic. Homoscedastic means same spread. When you hear homo, think same. When you hear scedastic, think spread. So same spread, homoscedasticity, and that's what I'm showing here with the yellow lines. Then we have the red line going through it saying it's somewhat linear. I know it's not perfect. Transformations don't fix the world. This is real data. Oh yeah, homoscedasticity. Hey, Kai, good to see you here. And this is basically doing a regression. This is the senior level class, and this is what we'll be doing in 201, and it's the theme of 320. So you can see the carryover of topics that we learn, and sometimes a transformation can take our original data, which I think he shows right here. Here's the original data, and create a better relationship that's going to express the data better. If you have questions, drop them in the chat. This is the only question we have right now. So Kaya and Brianna, drop a question in the chat and we can work it, whether it be a review question or a homework or pivot, whatever you like. We do have a video on the pivot, but whatever you're wondering, because it's open questions after this. So let's go back here to R and look at the original question, which set us down this road of talking about the Box Cox transformation. Consider why is a Box Cox transformation unhelpful with Canadian gas data. I suggest plotting the series and attempting a transformation, see if there's any difference. Okay, so do we have Canadian gas? We don't. Let's load in all the stuff above. There's the Canadian gas. We should have it now. There's the Canadian gas. Let's go ahead and auto plot it. And here's the Canadian gas. I suggest plotting the series and attempting a transformation and see why see if there are any differences between the series and the last two that cause issue. A simple transformation won't solve. Okay. Well, if you look, we got this lack of linearity. So there's a lack of linearity, and there's a change in spread. It goes line, flat line, curve in the middle. A lot of linearity issues. So the way we do the transformation, we're going to use the FPP3 methods. So he's going right here, doing the transformation. This one selects the transformation, the features Guerrero, and he's choosing the lambda based on that. So he's pulling the Guerrero right there. So he's just storing his lambda. Well, we can do the same methods and see what it suggests. So we are literally going to have it suggest for us the value. Could you go over p-values and know? Yeah, of course. We'll talk about p-values next year. Let me put that on the list. P-values for test. Let's say test prep, exam 1 prep, p-values. Good question. P-values. You got it. We'll be doing that here in about 5-6 minutes. And so I'm going to use the exact same methodology right here. This is going to pipe it through to grab a feature on it. Canadian Gas has the value volume, and the feature we're grabbing from it is the Guerrero. I believe that's the name of the person who did it. We're going to pull the lambda, and that should store the lambda value. That is an optimum. So the code I just ran finds the optimum value of lambda to transform this. I'll talk about how do you know whether a transformation is necessary. It can always be necessary. So here's such a great question, Colton, right there. So a transformation is always a possibility. Is it necessary? I would say it's necessary when it allows us to create a better model. Transformations are a good idea when we can create a better model with the transformed data. So when can you try transformations? Anytime. When are they a good idea? When you can make a better model. What is a better model? Up for interpretation. So that's the hardest part about statistics is when do we use this? Well, we can use it at any time. It's always a tool in our toolbox to try to transform the data to achieve a better model. And then we would compare the two models. So we need model comparison metrics. That's a key thing, especially we learn in 320, like RMSE 201, R squared. So we need some way to compare the models then and say, is this a better model? And we can look at it via the plots. So we're going to do that right here to think, is it a better model? We're literally going to take the same code right here. And let's go and drop this in. We're going to auto plot our data. We're going to go here to the auto plot with the Box Cox transformation on the volume. And we're going to use the title. Look at that, such pretty stuff. And we're going to go to not transformed gas. We're going to go Canadian gas, no Australian gas today, with a lambda. And it should have the lambda value we saw. Oh, it doesn't like that LaTeX stuff. So we're going to move out all this LaTeX stuff right here. It's mad about that. I've actually never used that sort of notation before. No package called, so title. Oh, I need to get that package. So install.packages. There we go. And then we need to load that library. So now I can do it. And that package is called LaTeX Express. Never used it before. And now it should work. Never used that one. Oh, because it's got the little lambda symbol, rather. That's how it's doing it. And so here's what we need to look at. What do you notice between these two? So what are two things that I said the transformation could fix? What do you notice? What are two things that I said the transformation could fix? What are two things that I said the transformation could fix? So when we're talking about the transformation, I was like, we are trying to achieve maybe two things right here. What are two things that linearity would be great to achieve? Great job, Colton, right there. It'd be good to achieve a linear, like QQ, straight enough, no outliers. Back to 201. We want a linear relationship that's good to achieve, and we also want the yellow bands right there, the two concepts being shown. So we want, and this is why 201, if you're listening in, QQ, straight enough, no outliers. We're still talking about that. And in chapter 7, plot doesn't thicken. We want the same sort of bands or spread of the data. So when you look at this and express this in your own words, here's the original data. So we should be able to go here to plus GG title, and we should say original data. There's the original data. And easy, no, I got to load my other library. Library GG easy. There we go. And then easy center title. I love everything to look nice. So there's my original data. Isn't that association is applied to all relationships with while linearity is only. Ooh, let me unhappy refrigerator. Ooh, let me see right here. Isn't it that association is applied to all relationships, correct? While linearity is something we only talk about between two quantitative variables. Unhappy refrigerator, thank you for being here. So good answer right there. Great answers. And this is 201 related. Correlation only applies to what? Correlation, because we're talking about a scatter plot right here. We can say two things are associated. Correlation would only apply to what? And that's a good answer right there, because correlation only applies to linear ideas, and linearity only applies to what? So unhappy refrigerator on a great track of thought right there. That association can be any two variables. When knowing one variable gives you information about another, those two variables are associated for whatever reason. But the idea of linearity or idea of linear relationships between variables that are correlated is only between two what variables, which could be done in a scatter plot. 201 question right here. And I'm going to make a graphic right here as we do this. Where's GG range? So think about that. Correlation only applies to what? Correlation only applies to what? Where's GG range? What? Do I not have GG plot 2? Where is GG range? GG pub R. You gotta know all your packages. You gotta know what you're looking for. P1. There we go. So Colton, why would I show it this way? And I'd maybe show a bit more. Correlation is only tied with linearity. I think it's because this is called correlation coefficient. Yep, it's only tied to two quantitative variables right here. So this is the optimum lambda right here. So this is the optimum lambda, and I don't want to fully say the answer, but Colton, do you see kind of what's going on right here? Like here is, I mean, I could even call it optimum lambda. Like this is selected via the program kind of finding the optimum. So optimum lambda, and so lambda value. And so here's the optimum lambda value. Here's the original data. There's the optimum lambda. That's the title. I should be able to go to easy center title. I don't like my title not to be centered. That worked, it looks like. Okay, that looks, and there we go. Maybe. Yeah, and remember the two things we're trying to say we're trying to I don't want to say the full answers, but remember what we're trying to fix. Remember the points of transformations. Why would we use a transformation? And if this is, and so you could try other values. I think I know how to make it in rows and columns. Let me try right here. So I'm just going to go right here, do the following, and we could literally take this right here, drop down the code, take this right here. We could try a lambda of 0, and lambda equals round 0 to 2. Sure, why not? And that's going to be P4, and then a lambda of 1, and round 1 to that. And I think that's got it. That's P3. Will that work? There we go. And so here's other values. And so when you look at this, funny enough, that lambda is 0. I don't know. Here's the optimum lambda. Here's other values. And this is how we can express ideas. And once again, you might need to take pictures on your own, because sometimes when it knits, it doesn't turn out so perfect. But think about what we're trying to do, Colton, right here. We're trying to communicate ideas on whether or not a transformation would be a good idea. So we can use the optimum value. We could use the lambda of 0, because that's a unique one that takes the log of it. Especially, this is getting very tight in here. That's getting more spread out. Still got issues of nonlinearity. See, now I'm interpreting it. I just can't help myself. But does this make sense what this is asking, Colton, right here, to talk about possible values of transformation, looking at the original data, and then it maybe makes some graphic right here that compares them and looks at it. One last thing. Can I change the autoplot color? I should be able to. Autoplot. Ooh. Yes. Yes. Of course. You gotta have different colors. I mean, come on. Sure, you know what we'll do? We'll make all the transformed ones. This is how we'll identify between transformed and non-transformed. And here's the original P1. It's not an extra argument. There we go. Or you can make it UT related. So yeah, this right here, there's the original data. So then the question becomes, are any of these really better? And you just want to think about ways to express and communicate ideas. And, you know, work with this on your own right here. Once again, the main way I got this code right here is I went to the book. The book is an absolute amazing way to get great code. You can just copy the code. So take a look at the book. Try doing these examples right here. Try running through. The book has such good information on the Guerrero feature. Can be used to find the value of lambda for you. It tries to optimize that lambda to create the relationships we need to look for in the data. And he talks about the way the lambda transformation works, which we'll be covering in class. So great questions right there, Colton. We're going to go to some p-value talk, which we learn in all of our classes. Let's head over to the main screen. Colton, great question. That was a lot of fun right there. People know I love making graphics. Like I just, you know, I'm like, okay, we got to color set graphic. We got to do something to it. So think about how you can make your graphics look great. Think about how you can communicate ideas. And that's the goal of it. The goal of data, the goal of, you know, learning statistics is to give data context. 201 question right there. Talking about data, we need to know what p-values are. So let's head over here to talk about p-values and the test. Oh my gosh, the test. So we're going to talk about some p-values for Stat 201 and Exam 1 prep. Let's go do this. Okay, so first thing we need to know is what is a p-value? Now, we don't go too detailed on p-values on the first test. So your knowledge of p-values here doesn't have to be too extreme, but a p-value is the probability of our results or results more extreme happening by random chance variation given the null is true. Now, this gets more complicated quickly when you realize that different p-values mean different things, but they always mean one consistent thing. P-value below 0.05 equals what? This is something we need to know. Who knows in the chat right now for 100 points? A p-value below 0.05 means this. You need to know this like that. You can be like, oh, it's below 0.05, it's this. So what does a p-value below 0.05 mean? Like we need to be like, oh, it's below 0.05, it is this. Like you should, when you hear below 0.05, you think this. That's very important for this test here. So we're doing a little bit of, you know, as we like to do, teaching to the test moments. What does p-value below 0.05 mean? That would mean the p-value itself is Kristen, this is good review. I'm going a little more detailed on this. I can teach like directly to the test or teach the concepts. This is a little more conceptual, and then I'll teach directly to the test. So statistically significant. What does statistically significant mean? Or statistical significance? Statistically significant. Statistically significant means unlikely by random chance. There's a Canvas content that kind of goes over that when a p-value is statistically significant, we wouldn't say it's due to random chance. We would say it's unlikely due to random chance. So what we need to think about here is, say that 5 times fast. Statistically significant means unlikely by random chance, or the probability of our results more extreme happening by random chance variation given that the null is true. So when we think about the 2 times we've used it so far, we've used p-values 2 times. And here's what you need to think about, especially for this test. The first time you heard about it, first time was the normal curve, right? The very first time you heard about it was the normal curve. We talked about the normal curve and p-values, statistical significance. Now I can say it. Hey, statistical significance, statistical significance. I can't do it. So when we talk about p-values in the normal curve, we can do a test. All p-values are relative to a test we are doing to see if the results are statistically significant. So p-values are not just related to the normal curve. It's that we are doing a what with the normal curve. Normal curve, where we did a something of fit test. So remember this test we did? We called it a something of fit test because remember we go here and Kristen, you got it. That is the test we are doing. We're doing a goodness of fit test. So what does the goodness of fit test see? Just think about why we call it a goodness of fit test. So it's a test that gives us a p-value. And so we're looking at the result of this test to see if it's a what. Just think about it sees the goodness of fit, sees if what? Just kind of the goodness of fit sees, just use the words of it. It sees for that data is the what? If the normal curve is a good fit, is the normal curve a good fit? Great job, Kristen, right there. Is the normal curve a good fit? That's what the goodness of fit test does. Is the normal curve a good fit? That's what the goodness of fit test does. So the best or the easiest way to understand this one is if the p-value here is low, so below 0.05, bad fit. 0.05 or higher, good fit. So if it is a good fit, we will see a p-value of 0.05 or higher. So just give a guess. We're not doing the test right now, but just use the color coding maybe to help, but guess the p-value if you ran this on that distribution. Like if you said, let's do a goodness of fit test on this distribution right here to see if the normal curve is a good fit. What do you think the p-value would be on the goodness of fit test? So remember, on this one, and this is only for this test right here, if it's below 0.05, it indicates a bad fit. It might not be exactly 0.05. Think, careful. I'll let you keep going. Kristen, 100 points. You got this. Maybe not exactly 0.5. Yeah, I would go with that. 0.05 or higher. I'd go with that. Maybe like 0.68, 0.98, 0.42, but something higher than 0.05, right? Because the test would probably come back that this is a good fit. But then go over here and kind of do a different distribution, which we could throw this back to what we were just doing, fit a normal curve on top of this, and this would come back with a p-value of probably what? Like this one right here, hypothetically, could have a p-value of 0.48, and that's just telling us that we still believe it's a good fit. It never goes past 1 because p-values are probabilities. Great questions. P-values are probabilities, so they're only contained between 0 and 1. It can't go above 1 because it's a probability of observing what we observe or results more extreme. And due to random chance, given the null is true. This might have a p-value of 0.001. So you would be led to believe what for this second one? For the second one, you'd be led to believe that the normal curve is a what fit for that distribution. Think about why it's called goodness of fit again. You'd be led to believe via the results that the normal curve is a what fit for that distribution. Be like, I've got some evidence that the normal curve for this is a what. And this only relates to this test. We're going to do the second one. It's a bad fit. So when you run the goodness of fit test, the question is the normal curve a good fit? And this result for this distribution comes back as a bad fit, where the one in the previous example comes back that it is probably a good fit. Or we have reason to believe that, or we fail to reject the null. We try to talk in normal terms sometimes where we say, it looks like the normal curve is a pretty good fit. I don't have evidence it's a bad fit. So I would continue to believe that the normal curve is a good way to express that distribution. So this is only for the goodness of fit test. And what does the goodness of fit test look at? The goodness of fit test only looks at what? This is the first time we looked at it. And so what does the goodness of fit test look at? This is p-values for the goodness of fit test. So what does the goodness of fit test look at? What does the goodness of fit test look at? And then putting a second note right here because we're about to do the second topic for correlation. It looks at the normal curve and asks, is the normal curve a good fit? So the second time we have p-values, it's for correlation. And with correlation p-values work the following way. Once again, a p-value is the probability of our results or results from our stream having by random chance variation given that the null is true. But in correlation, so this is the second time, and we have here correlation. Whoa. What did I do? I did some really quick accent stuff right there. Correlation assumes no correlation to start, and we look for evidence of correlation. So when you think about this, if there's no correlation, let's assume there's no correlation to start. And I said something likely, like a very high likely thing to see right here. That's very likely to see given no correlation. How would a plot look like something likely if there's no correlation? Like what would a plot look like? What's a likely result to see if there's no correlation? Just think, if you assume that there's no correlation to start, then what is a likely thing to see if there's no correlation? So we assume that there's no correlation, then we just think about what would be likely to see. Not that there's two different types of p-values. The p-value always tells us the probability of our results or results from our stream happening by random chance variation, given that the null is true. And the null hypothesis is that there is no correlation. We haven't talked about nulls really, but once again, we don't want to memorize the definition. We want to say, okay, wait, we are assuming, and like you're saying, that there's no correlation. So this would be a likely result to see. And the correlation value here is rather what now? So that's a likely thing to see. If there's no correlation, just tell me if there's no correlation, the correlation should be close to what? So this is a test to see if there is correlation. Let's put that right here. Test to see if evidence of correlation. This is a test to see. Would the correlation be high? The p-value is high, telling us that this is likely given there's no correlation. So this is a likely result given there's no correlation. And what is the value of no correlation? The value of no correlation would be a correlation close to what? The value of no correlation would be a value of correlation very close to what? So R is correlation, and we'd see a correlation close to 0. Kaya, great answer right there. More points in the chat. Keep those answers coming. Keep that practice coming. So correlations close to 0 are likely given there's no correlation. Does that make sense? So correlations, and we could even say negative. You might say, is that negative? Well, maybe it just slightly goes down. You can't really tell. Correlations close to 0. I don't want to go to Cortana. Correlations close to 0 are likely by random chance, given there's no correlation. Does that make sense to say a correlation close to 0 would be likely just by random dots, even if there is no correlation? I thought it was above 5. There's no correlation. Nope, it is. And double check. So definitely, Maria, good question right there. I thought it was above 0.05. There is no correlation. Double check. If you find a video, I'll even release a correction. But if you see a video where I've said the opposite, please let me know. 0.05 or above indicates to us that there's no correlation. Below 0.05 is evidence of correlation. Find out any video where I do the reverse, because I'd want to know. What would be unlikely to see? What would be unlikely to see if there's no correlation? If there's no correlation, what would be an unlikely result? If there is no correlation, what would be an unlikely? For the p-value or for R? Oh, well, R is just the strength of the correlation. So never go off statistical significance off of R. So what's the difference between R and p-values? R is the value of correlation. So R tells us the strength of the correlation. P-value, so good questions right here. Thank you so much. 100 points. Keep those questions coming. R indicates strength of correlation. So these are values of strength. The p-value over here is statistical significance. So the R values tell us the strength of the correlation. The p-values tell us the statistical significance. Does that make sense? So whenever we say like a correlation of something like correlation equals negative 0.80, that is a very strong negative correlation. Does that make sense? So the R value is the value of correlation. Like R tells you the value of correlation. So negative 0.80 is a strong, because it's closer to -1, and negative, that's the direction of it, correlation. So R is the value of correlation. The p-value is always telling us whether something is or is not statistically significant. So think about this. How would this correlation look? This correlation is going to be in great work right here. This is a tougher concept. It's going to look something like this. And you would tell me this result right here is very what by random chance, given there's no correlation. So yeah, this is a big, Kirsten, if you get this, a lot of people just don't understand p-values, which is all right. But this is a big concept. That result you see on the screen right there of a negative strong correlation like that is very what by random chance? Because the low p-value, which is statistically significant. It's statistically significant. Wait, so it's statistically significant because it's below 0.05, and that means it's very, put a U word right there. It means it's very, very what by random chance. Maria, it's good. Well, so no, this is unlikely by random chance. So the p-value tells us whether or not it's likely or unlikely by random chance. And so the p-value is the probability of our results or results we're seeing happening by random chance. And so we assume that there's no correlation. That is the starting assumption. And so this would be a what result by random chance. Think of a U word. Seeing this, if there's no correlation, is very what? If there's no correlation, the result we see right here is very, I like it, you might be seeing it, is very what by random chance. This result right here, if there is no correlation, was very what by random chance. Think of a U word. Boom, Kaya, right there, another 100 points. Unlikely. Think about this. This result right here, if there's no correlation, was very what? If there's no correlation, this result right here is very what? So this result, which we see right here, was very what by random chance? You'd say, well, this was very what right here. This result was a very what result if there's no correlation? It's very likely. It's like, well, I mean, if there's no correlation, that's what we probably should be seeing. We should see a very small correlation that looks pretty random. And this was pretty likely. Where the result down here on the bottom was very unlikely by random chance. Now, to go back and mention the other topic, what we assume right here for this is we assume that the normal curve is a good fit. So we could add that right here. We could just say, assume normal curve is good fit. So which of these looks like a likely result, the first or the second, if the normal curve is a good fit? To go back, oh, wow. Whoa! If we assume the normal curve is a good fit, which of these looks like a likely result, the first or the second? If we assume the normal curve is a good fit. Yeah, Maria, that's what I want to see. Kind of. Maria, Kristen, I can mention that in a moment. The first is, if the normal curve is a good fit, well, then that's probably what we should see up there at the top, right? But if the normal curve is a good fit, then down here, this would not be what we should see. We shouldn't see something like this. This would be unlikely to see. The normal curve looking like that on that is unlikely if the normal curve is a good fit. The top result is something likely to see if the normal curve is a good fit. It's more likely that the normal curve is the right fit when we look at the results that look like that. And this is the moments, like it's going to help for later in the class. Like this is the deeper understanding. If you followed through these steps right here and you've reached this point of understanding, you have a deeper understanding of these concepts. Once again, I want to repeat, and then I'm going to do Kristen's question right here. P-values just tell us what? So don't think about, it tells us if it's normal. It tells us if there's correlation. That's side topics. P-values just tell us what? P-values are just a way to look at what? So whenever you hear p-value, you'd say, someone's just looking to see if there's what for their data. So whenever you see p-values, you say, we're just looking at what? So don't think about normal. Don't think about correlation. P-values are just to tell you if there's what in your data. If your results are this. You can look at a p-value to tell if your results are this. Not if it's normal. Statistical significance, exactly. P-values just look at statistical significance because they're used in many, many different tests. So we can see if something is statistically significant, meaning it's unlikely by random chance. And we can do that here for correlation. And we can do that here for other things. So, Kristen, you're kind of right. So the higher the p-value, high p-values are, and this is only for testing correlation. When it comes to correlation, so please caveat this. Does that make sense? It's not like all high p-values are related to this. But generally speaking, high p-values would be associated with smaller correlations when it comes to testing correlation. Lower p-values would be associated with a higher value or higher strength of correlation. Does that make sense right there? And Maria, great answers in the chat right there. Perfect. Does this make sense right here that when it comes to correlation, higher p-values would be often paired with very small values of correlation because that's what's likely when it comes to correlation. When it comes to correlation, lower p-values would be associated with stronger. So once again, we could do this right here, kind of the same sort of strength, but going up. And what do you think the p-value for this result would be? So this test right here would probably have a p-value of what? Like, what do you think the p-value of that would be? Like that correlation right there probably has a p-value of what? The p-value for that is probably what? Just take a guess at what it is. So think like, is that likely by random chance given there's no correlation, or Below 0.05, definitely, right? It's going to be something like a p-value of 0.000001 or something like that. And then the correlation value, take a guess. It's very unlikely by random chance, right? That looks unlikely by random chance if there's no correlation. And then just take a guess at the value of correlation on that. So you should be able to tell a decent guess at the strength. You should know the direction of it. So what do you think the value of correlation would be, which tells us the strength and the direction mostly? The value of correlation is going to be closer to what? Closer. Well, be careful. So, Kristen, give an exact guess. You got this. Just take a. Hey, Kayla, good to see you here. Assignment 5. You bet. Let's do that. Close to 1, and so you said it right there. Why close to 1? Because it's positive. Does that make sense? So you figured out the direction right there is positive. So you're like, it's going to be closer to 1 right there. So that's what we want to start thinking about. I'm going to show you one last thing, which don't let it scare you. I want you to think about this. Let's look at something you haven't seen, which is something that is in 320, which we just did. Watch this. I'm going to tell you the null hypothesis for this data. And then I want you to tell me if you think that we should go against the null, if we should believe otherwise. So we're going to look at, let's look at heights. Heights, gender, and you're about to see a test you've never seen. And this is showing you that this will help with other classes. So here, let me show you. Here is a p-value, and here's a test you haven't heard yet. What do you think? So Kayla's seen this. This is a review for Kayla. The null is a starting assumption, like there's no correlation or the normal curve's a good fit. So the null is a starting assumption. I'm going to start out believing that there's no differences in the average height of males and females. So if that's my starting assumption, does this result that I see right here, this difference, look likely or unlikely by random chance? So this right here is a test we will do at the end of 201. You see right here, I'm looking at males and females' heights, and my starting assumption is that there's no difference. Does my result right here seem likely or unlikely? This difference I observe, where females were about 5'5" and males were about 5'11", does this result seem likely or unlikely by random chance? That's what the p-value tells us. P-value tells us likely or unlikely by random chance. Does this result look likely or unlikely by random chance? Just look at the p-value. Oh, wait, Kale. Reverse it. Remember, low p-value. So the low p-value means it's what by random chance? Unlikely, right? Because the low p-value means unlikely by random chance. Think about it like winning the lottery. If I tell you you have a 0 probability of winning the lottery, you're like, I'm not going to win the lottery. Does that make sense? If the probability is 0 of something, it's not going to happen. Does that make sense to say unlikely? No, this is the practice, 100 points. This is why we do this. Because remember, low p-value means unlikely. You're talking about the probability of it. You're saying that's unlikely right there because it's low. So think about this. My starting assumption here is that there's no difference between males and females. What do you think I have evidence for? Just interpret the results. So this is good practice for Kayla, and then we're going to do Kayla's question next right here. So if I have a starting assumption that there is no difference between the heights of males and females, I probably have evidence for what when I'm looking at this test result, which is the end of 201 and the start of 320. I probably would say there's good evidence that there's what between males and females right here. A difference in what? How would I interpret it to say, I started out believing there's no difference in the heights of males and females. Looks to me that my test shows evidence of what? And that's what the p-value is saying. It's unlikely that there really is no difference between males and females. So I'd have evidence of what? I would say I have evidence to conclude, and just wait for it, I reject the null hypothesis, and that's the way we talk towards the end of 201. I reject the null hypothesis. There is evidence of a difference between the heights of males and females. Just shocking conclusion about the world that we have evidence of a difference between the heights of males and females. Not quite correlation, because remember, male and female is not quantitative, and to do correlation, we need 2 quantitative variables. So remember, correlation only goes to 2 quantitative variables. So good review right there, Maria and everybody. Correlation is only 2 quantitative variables, so we can't say they're correlated. We could say they are associated. Next question. So we kind of went a little bit more advanced there at the end, kind of previewing some 320 and connecting topics for later in 201. But we're going to do some 320 right now, so stay tuned. You're probably going to hear some concepts related to 201. It's not like we directly do them in 201, but there's a lot of 320 concepts in 201. So stay tuned. Let's go to the assignments right here. Simple linear regression. Kayla, we're actually going to talk about regression in 320, a class called regression. 2 quantitative errors, no outliers, straight enough. QQ, straight enough, no outliers. Great job, Maria, right there. That's worth 100 points. QQ, straight enough, no outliers. And Kayla was wondering about assignment 5 today. Yeah, which one do you want to do on assignment 5, Kayla? Let me know assignment 5 question what? Just put like Q1, Q1C1, Q1C13, Q1C15, Q1C18, Q1C110. It's about a billion Q1C1 questions. But just mention which question you want to do on assignment 5. And number 1. Ooh, this is a good one right here. Okay, you'll need to load in 1A, right? Okay, let's talk about this. Let's go over here to the main screen. Here we go. Okay, the following data uses the EX6 NFL data set. Okay, so we need to load up reg class right here. Oh, I didn't take a timestamp. 5135. So BS 320, assignment 5, starting the assignment. Okay. The fact that I've been in the in math class for 24 hours. Oh no, Maria, take a break, relax, drink some coffee. Kristen, my gosh, up to Tiny Evil Brian tier. That's a new tier right there. You're welcome, Kristen. Excellent work. Another 100 points. Why not? So have a great day. Great work today. So the why, we need to load in our data set. Data ex3.nfl. Gonna load in the data after I clear all the data there. And now we've got the data loaded in total. And so now we've got the EX3 NFL data set loaded in. Once again, if you're worried about this, you too, Marie, have a great day. So more points. So I just like hitting the points button. When you look at this right here, these are different teams, the amount of wins they have, the amount of total yards, all different variables just over different seasons. So you could actually look at, Arizona, you could look at Washington, all these different teams, and just look at the data set, whether it be Tampa Bay, Tennessee, San Diego, San Francisco. We can look at all these teams. So just make sure you understand what data you have. So we've got the data loading it in. I loaded it up there. That's totally fine. What does next year's wins being integer values violate? Why does it violate the assumption of the normality of the residuals? And that's E right there, the residuals being distributed normally with a mean of 0 and a standard deviation of constant. This is a big question here, Kayla. So this actually goes to 201. And it's very interesting if you look at what we've been doing right here with this equation. Actually, it goes to kind of that. It goes to so many things we've been talking about right here. And if you remember from 201, does it let me carry that notation over? Perfect. So this is back to 201 a little bit. I always try to say how these things connect, that if you remember a lot of 201, it'll be a huge help for this. So ignore the E for a moment. Ignore the E for a moment. What does, here we're going to erase a lot of things on this. What does the capital N there represent? What does the capital N represent? What does the capital N represent? The capital N represents that the E, which are residuals, the normally distributed, right? So that's the shape of it. So that means this should be normally shaped. And then what does the first number represent? What does the first number represent of the distribution? So the first number of the distribution represents what its what is. Like this is the blank of the distribution. The mean, Kayla, great answers right here. And then the last number represents the what. So what two things do we pair together, which are good to know? And then the standard deviation is like, I got this. So we're saying a certain thing right here, a certain values or a certain amount of values will be distributed this way. Like they'll fall under the distribution this way. What are these values we're talking about right here? We are actually talking about, we have a picture from yesterday, we're talking about the residuals. A residual is merely a what when we talk about the model. When we talk about a residual, these are the sums of squares right now. A residual is how much our model what's by. So we're talking about these values right here. What is a residual? A residual is basically how much our model what's by. So there's residual equals actual, it's how much we miss by. So the residual is, you look at, here's your model making a prediction, which is the line. And then we have here the actual point, and the residual is the distance we are away. Like, you want your residuals to be small. Actual minus predicted, exactly. You know what's really interesting, Kayla, is what we can do is we can actually make, and let's go look at this. Here's the answer. Well, we're going to do a little bit of coding because we love coding. And let's go here to Q. Oh, did I delete something I shouldn't? No. There we go. Really? Q1A. And we're going to go here to M, save into LM. The Y variable of interest is next year's wins. I think we asked later on, was the strongest correlations. So we really only need it as the Y variable of interest. I love coding. Exactly. I do love coding. It's like, it answers, you can get so many questions answered so immediately. If we predict next year's wins, because we could look at what's highly correlated, let's just say example work, just show issues. And then we need to go here and do data equals EX3 NFL. Oh, next year's wins not found. Dun, dun, dun. And no, we can cheat. Attach EX3 NFL. There it is. Where's the typo on that? Oh, wait, what? Ooh, where was the typo? Oh, how did I do that? I did year wins. I did next year wins. Next year wins, not next year's wins. There is an S on that, and I missed it on the first time I typed it, and that's why it said next year wins not found. It's years. So there you go. Typos, problems. Attach attaches all the vectors to the global environment so I can use them with the autocomplete. Some people don't like doing it because it can create aliases where things are on top of each other with the same name. I don't think it's the end of the world. You can get all your residuals with this. That is the code to get all your residuals. Do not print stuff like this. Do not knit this. This is excessive output. Do not knit things like this. So I write things in here. I'm not trying to create problems for people, but this is where, so Kayla, what do I not want you to do when you create your assignment? Because this will create, no one's going to read this. I'm just looking at this. I am not creating something. I'm showing examples. Do not knit that. That will create excessive output. Do not knit this. I'm stating it multiple times. Do not leave that in. You'd want to comment this out right here before knitting. If you're looking at something like that, do not knit that. Do not put that into your assignment. That'll create excessive output. You always want to look through and think, do not put excessive output. And you can always delete after knitting. So if you knit something, you're like, I don't like that. You can just delete it from the Word document. So do not knit things like that. Do not knit things like that. And so here's the issue. This is the easiest way to summarize the issue. I want you to look at these numbers right here, Kayla. Let me sort the table. These numbers have a lot of decimals, right, Kayla? Do you notice like how decimal precise these numbers are? And then I want you to think about randomness. This number occurred 10 times. Look at how decimal precise this number is. Does it seem that a decimal precise number like this, negative 4.58728185719763, would occur 10 times out of 320? It occurred something like 3% of the time. This occurred 3% of the time, and I'm to believe this is random. Would that number down to that precision occur? That doesn't seem that random, does it? And this is where we get to the concept. That seems crazy that would occur. And then this number occurred 8 times. You'd expect a bunch of unique occurrences, right? Like here's a bunch of unique occurrences where those only occurred 1 time. So when you look at this right here, especially when we just look at the tail, which could be a good way to communicate the numbers, these numbers occurred like 10, 8, 24, 30. This is about 10% of the residuals are occurring with five residual values. So when we talk about the residuals, which are this right here, there's 10 of them, maybe even twice, down to that decimal accuracy. Like, yeah, if one of them occurred twice, I'd be like, that's weird, because it's down to like 10 decimal place accuracy. Like, there's one residual that has like the exact same I mean, like, okay, maybe that's, yeah, possible. Like, yeah, sure. But is there 10 that have this exact? We're saying there's 10 points in this data set that have the exact same residual difference. Does that make sense, Kayla, right there? Like, this is what we're communicating right now with that idea, that there's 10 points that have that exact same residual distance. 10 points. 10 points. It's not even 10. So it looks crazy in there. There's like this sort of pattern. And that's because, especially, and remember I just said pattern. If we look at our model right here, the y values have a what to them? Because y is integer, because y is an integer-based value, y has a what in it. So look at how y looks. If you look at it and the even spacing of it, as you go up in the y, because it's integer-based, y has a what in it. The y variable has a what in it, because if I tell you 1, 2, 3, 4, 5, 6, you'll say the next number. What do you say when I say 1, 2, 3, 4, 5, 6? What do you say to me? What would you say next, Kayla? 1, 2, 3, 4, 5, 6. I bet you'll say something next. And I bet that number is what? You don't know, wait, 1, 2, 3, 4, 5, 6. Just say that to your kids. Be like, finish this phrase. 1, 2, 3, 4, 5, 6. And they'd say, what next? So 7. Because there's a what in the data. Because it's integer based, because you're seeing it, there's a what in the data. Think of a P word. Because it's integer based, there's a what in the data. Think about there. Think of a P word. Because it's integer based, there is a this in the data. Oh, that 7 comes next because we've found a what in the data. Like we have a this in our data. 7 comes next because there's a what in the data. Think about this. You say, oh, you found the blank in the data. You found that there's a something starts with a P. Pattern, exactly 100 points. There's a pattern. So if there's a pattern in our data, that pattern might go through into the residuals. So the residuals oftentimes carry the patterns of our data. So these residuals right here have a pattern because the y has a pattern. But here's the issue. The residuals should look what, Kayla? The residuals should look random. So our residuals are supposed to follow a random normal distribution. And when we say that the residuals follow a random normal distribution, so this is the random normal, then if they are supposed to be centered at 0 and have a constant standard deviation, that's what that stands for, constant standard deviation, like one value of standard deviation equal spread throughout the model, we wouldn't see this because random normal residuals shouldn't repeat. If I'm randomly plucking values from here, I'm not going to get the same value 10 times. Does that make sense? That this is not really random. So the issue is, and there's like a summation of it. And so you got to write like a little bit of like a few sentences on this. Our y value has a pattern in it. That pattern in the y value carries over into the residuals because the residuals will sometimes carry through the patterns in the data. And since the residuals have a pattern, they are not following a random normal. And this can be evidenced by us seeing repeated values of residuals that would be not likely to see if we're randomly getting residuals. So the residuals don't look to be truly random normal, and that's the issue right here, because of the pattern in the integer-based value of the data. Does that make sense, Kayla? What are you thinking? Your thoughts on this? We want the residuals to be random normal, but the integer-based value of the y has a pattern inherent to it, and that pattern in the y carries through as a pattern into the residuals, and patterns in the residuals are not random normal. How's that sound? Kind of just rephrasing right there. But that's the whole idea of we want the residuals to be random, and they're not random. So that's the big problem. Like, don't just write that. But that's summation. It does make sense. Yeah, and ask more questions if you got it. This actually is your major conditions. I want to mention one last thing here, Kayla, because I want you to think about this. We want the residuals to be around 0. Look at this model right here, Kayla, and tell me, in the green region, the residuals are what? In the red region, the residuals are what? In the green region, the residuals are what? So this is an actual model right here, and we want the residuals to be centered at 0. So in the green, oh wow, it's got the white pen, I think. Microsoft Word needs to fix their program. So in the green region, the residuals are what? The green are positive, right? So interestingly enough, that condition right there of the residuals should have a mean of 0, and that should be at all points, is actually the what condition. So this is good to know. The residuals having a mean of 0 is the what condition. So the residuals shouldn't be mostly positive. They should have a mean of 0 because the residuals don't have a mean of 0 here. The mean of these residuals is positive. Like if you average these things, it'd be positive. If you average these, it'd be negative. If you average these, it'd be positive. So this right here, the mean of 0 is actually the what condition. If we follow that, the mean of 0 suggests that the what is a good fit for it. So we're going back to QQ something. So the mean of 0 is actually the what condition for our data. The mean of 0 is actually the what condition. It's linearity. That's what it is. And tell me this. If we're saying next that it needs to have one value for the standard deviation, does this plot right here look to have one standard deviation value? Does this plot look here to have one standard deviation value for the residuals? Do the residuals look to have one standard deviation value right here? So do the residuals right here look to have one standard deviation value, like one constant standard deviation? Do they look to have a constant standard, like one value would describe the standard deviation? So we're saying the residuals of it, no, they don't. So QQ straight enough, no outliers. This is the what we call into a 1, which heteroscedasticity is an issue. QQ straight enough, no outliers, and that whole thing of constant variance or one value of standard deviation is the what condition right here in 201. So good review for 201 upcoming. That right there says that we need the what to not what. QQ straight enough, no outliers. Then we got time for another question. We're doing some forward. Plot doesn't thicken. So this right here is literally the plot doesn't thicken condition. Does that make sense, Kayla? So we want them to follow a normal distribution, and we want the line to be centered around it. This would have linearity. So there's like a mean of 0. If you average these together, they would average to 0, but there's not a constant spread to it. Like the residuals don't have a constant variance. So there's heteroscedasticity in the residuals. So really good review right here, understanding what is going on. And this is what we'll be covering this week, later today especially. Kayla, do you want to do the next question? That's a good lot of concepts right here. Understanding what residuals are, understanding the model, understanding heteroscedasticity issues, understanding the linearity condition. Very important things to like build our toolbox on our understanding for the topics. We'll head over here. We got time for at least one more. So drop those questions in the chat if you got them. Let's see. If you have questions, let me know. Yeah, let's keep going. You bet. Okay. See if there's anything on Discord. Wordle channel has taken off on the Discord. Okay, let's look at the next question. Okay, here we go. Let's go check it out. Find the 6 variables most correlated that have the strongest correlation. Now watch out. Here's where we run into a problem. Do you know what argument we need to use, Kayla, to find the strongest correlation? This is a paradox. Don't think the most obvious answer right here. To find the 6 strongest correlations with next year's wins, what argument should we use? So we're going to do the all correlation. Magnitude. Great answer right there, Kelly. You're right. You would say strongest, but strongest puts from most negative to most positive. So it just does it by order of strength from most negative to most positive in strength terms. So we need to put here all correlations. We need to choose the data set we're working with. That runs. Ooh, taking a moment. It's thinking. Why is it taking a moment? Probably, oh, because it did about 9,000 correlations. Ayo, Adam, good to see you here. Asking any questions, we got them. So we want to look at interest equals next year's wins. And then we want to go here to sorted equals magnitude. I want to point this out. When you write out arguments, let it autocomplete, because then you'll know you spelled them correctly. Autocomplete usually is your best friend. And this should do it right here. But Kayla, what could we put around this to not get so much output? What could I do? There's multiple ways I can solve this right now, but what could I do to make it look better? Who knows? Had to sneeze. Sorry. Everyone's like, where'd Brian go? You can store it into object X right here, and Kayla said to use head. Great answer right there. The head of a function will do this right here, and that's got it. I'm getting more message on part 1 and on assignment 4, but I still get an answer. Warnings just appear. You can always suppress the warnings. So you can go here to suppress warnings. And there we go right there. It won't do anything to this, but Adam, that works right there. If you have any questions, let me know. But here we go with the 6 strongest correlations. Extra points. Wow. Next year's wins is highly based on extra points. You know what I've noticed about NFL teams? I think NFL teams have very little turnover. If you know anything about the NFL teams have very little turnover on their their kickers. So maybe teams that have really good kickers generally keep those like extra point kickers and stuff. So maybe there's a very high correlation right there. Awesome. Yep, the suppress warnings is pretty good. We don't need it on this, but it just suppress warnings is if we have them. Extra offensive extra points attempted. So you want to attempt them. And then we see a negative one right here with offensive yards points. Don't even know what that is. These are the 6 right here, most correlated things. Oh, Kristen, feel free to ask questions. We got open questions. We're talking about some correlations right here. And so all of these correlations but one are what? So we can see there's a what correlation. They are statistically significant. So there's a statistically significant correlation between all 6 of these. That's because the p-values right here. And if you look at these are like 1, 2, 3, 4, 5, 6, 7, 8. That's the p-value right there. I might have made a typo at the end. But this is a very, very, very statistically significant relationship that if you know the extra points a team is making, that'll tell you something about their next year's wins. So look at the teams that are making a bunch of extra points and you'd be like, probably going to do pretty well next year. Now, it doesn't mean, and then, so we see, so the p-value tells us statistical significance, and these are moderately weak, I would say. They're like 0.5 is moderate. The decimals on the pivot, we'll show that here next. Great question, Kristen. These are moderate weak. Moderate's around 0.5. Perfect is 1 or -1. And like, once again, the sign doesn't matter. That's only direction. Rock knows. It doesn't matter. Sign just tells us direction, doesn't tell us strength. So this is sorted by magnitude. And we see right here, moderately weak, because the weak is close to 0. So moderate 0.5, moderate weak. There's no defined, like when someone says moderate, what do they mean? Well, they should probably mean something closer to 0.5. Strong compared. Yeah, good point right there, Kale. 100 points. Stronger compared to the rest. Yep. They are the strongest. So they are the strongest in the data set. And yeah, good stuff right here. So just kind of talk about those or, find the 6. Those are the 6 right there. That's how we find the strongest correlations. Let's head back over here. Let's show how to round in pivot tables. Okay. And Kayla, we might have time for another one, so stay tuned. We could do some rounding on the pivot tables. So 114, 115, 05. Stat tool 1, rounding pivot tables, rounding values. Okay, so let's go look at some rounding of values on the pivot tables. Let me close out this. Okay, here we go. Let's go do it. Okay. So the number one thing we need to know is when we create our pivot table, the easiest way to round it is when you start off rounding your values. So I would highly suggest rounding your values to start. So we're going to create the pivot table. We go through this a little bit slower on the Friday video, so check that one out. I'm going to go in here and go to Insert Pivot Table, and we're just going to put it in. and then we're going to find our value. Awesome. Have a great day. Hope your day's going well. Have fun picking up the oldest. We're going to put in GPA right here. And I'm going to drop GPA down to here into the values. I'm going to disappear so you can see what I did. And I put GPA into values, and this is where the rounding begins. This right here doesn't need rounding, but it's the sum of the GPA. Can you do me a favor to then check a graph I made for myself? Yeah, yep. Adam, send it my way, and I can take a look. I could look on the Discord if you send it that way and look at it. I'm going to go to the average right here, and this is the value field setting. And the main question right now is, how do we round values? So this is ridiculous. It's higher than my GPA, but we don't want all these decimals. So go here and go to home and then delete the decimals. Now you could do this individually for each one. I think GPA should be to 2 decimals. You could go by Brian's argument of always include one more than you think. That's not bad, but I think GPA should be at 2 decimals. I think 3 is fine. I would not do 1 because someone who has a 3.21 or 3.24, usually people give that extra decimal right there. So I'd probably do this right here. Now, if you didn't round to start and you started splitting it up, so let's go back to where we can view it. If you started splitting things up right here, you would then need to do the following. Either click each individual value to round, which is a tedious process, or click one value, hold shift, and click the lowest value. Now with all values selected, go here to the delete the decimal buttons and delete the decimals. Once again, it's easiest to do this if you have the value first changed at the start. Then all values that subsequently follow from it will be changed. So I do highly suggest choosing your decimal rounding to start, and then every subsequent value created from it will have that rounding. If you don't, you can always select all the values or do them individually. The tedious process would be to go here and round one down to what you want and just make sure it's consistent rounding. This is a way bigger, tedious process than going in here and selecting a value, selecting the other value, and deleting down decimals. Kristen, how does that look? Is that working good for you right there? Let me know if you were able to change the decimal places with under the home, the decimal changes. Make sure the values are selected in the pivot table, and that should do it. You got it. No, that's Kristen. Once you know it, it's pretty simple, and I appreciate you asking. Just, let everyone know. I'm always like, hey, Government Officer, swing by. And I know tons of people use these videos later, so you probably just helped out some students who are like, wait, how do we do this? And then it's like, oh, okay, that's how we do it. Just select the values. Cool. Let's go check this out. Let's go check out Adam. Thank you for sending me that message on Discord. Let me go look. Question about the graphic. Can you send me your full file? I might have the thing on this. Which number is this, Adam? Let me go look. Can you do me a favor and check this a graph I made for assignment 4? Which one is this again? It looks accurate. It seems accurate. Oh, here it is. I think it's question 2, right? For each of the following series, make a graph of the data. If transforming seems appropriate, do so and describe the effect. Show both the series and then the transform series. Comment on the changes to the series from transformation if one is used. Something weird with this. Something weird. So the problem is oh, I think I see the problem. It's question 1. Okay, let me go to question 1. Sorry. Consider the GDP of global economy. Which country has the highest GDP? How high was the GDP per capita changed over this time? Plot the GDP per capita for a section. Note, you won't be able to plot all countries at once. Plot the highest per capita and a few additional for comparison. So I would go right here and I'd include it's mad at me. It's always mad at me. It's always mad. I would do the comparison. Priya asks, can you go over 4 and 5 on the practice exam? Yeah, Priya, let's do that next year. We might end with that. That sounds good to do. I'll send you back some code here, Adam. We should definitely look at some comparison metrics right here. And so I'm going to send you back a code right here. Okay, good. I think you have the wrong country. And this shows it. Because I have Bahrain here. And so I think you have the wrong country. Hide user on channel. And so I'm going to send you back some code right here. And so, Adam, here's the big thing. It says, which country has the highest GDP? How has GDP changed per capita over time? Plot the GDP per capita for the selection of countries over time. Note, you won't be able to plot all countries. Plot the highest country per capita and a few additional for comparison purposes. So if you have the highest country right here, can you show me how to display the average of the quantitative variable in the pivot chart? Mm-hmm. You bet. We'll check that out here in a second again. Thank you, everyone, for being here. Let's go check this out. So I'm about to send you some code right here. But it looks like there's issues with that being the highest. And I sent you a thing to be able to compare them, but I'm not sure it's the highest. So to Braden's question right here, so we'll continue on this segment real quick. So to display the average, we need to change the what. So good review question right here. What do we need to change to display the average? To display the average, we need to change the what in our pivot table. So this is one of the first things we change. How do we get it to display average instead of something like count? So when we want to display something like average in our pivot table, we're going back in time right here. How do we get our pivot table to display something like average instead of count? So right now it says count. We need to go to the settings of the value field right here. So the value field setting right here is what we need to change. And then with the value field setting, we can change it from count to average right here. And now we can see it now shows the average. And once again, after this point, make sure to delete down the decimals. And there we go. We now have the decimal we want. And good stuff. And great question right there, Braden right there for asking. We're going to look at, we should be able to do 4, maybe 5. Let's go check it out. Okay, so we got review 1 coming up here in the chat. Some chill music. And so Stat Tool 1, Exam 1 review, practice or test question or review question 5. 4 to start. Review question 4. Mubot's got it in the chat. Here we go. I'll head over here to the main screen. Let's do it. Okay, so with the review exam right here, there is a key, and I do want to point this out. So don't worry. You're welcome, Brandon, right there. You're welcome. If you have questions on any of these, you can always go here to the practice test review, and I go over the questions on how to solve them, but we're going to solve them here. So this is question number 5 on how to solve it. But once again, check these out if you want. I'm going to solve question 4, and usually I'll solve it a different way, which is always a fun way to practice and to learn. So we're going here to the practice exam, and we're going to go down to question number 4. But do remember, if you're looking, wait, that you didn't cover the one we're trying to do right now, Brian, then there is the practice exam videos right there on the review page you see in the chat. So right here, we've got some reaction times. Do we change the number of this? We're always changing numbers on these exams. Changing numbers. Okay, so let's take a look right here. The reaction time of a hockey player. And so what do we have? Let's go grab it, bring it over here to a new page, and start working on it. Oh, no, Priya, that's the point. That's a lot of people don't know. That's Priya, 100 points. Don't worry, that's a lot of people don't know. That's why I show it. So that way, like, after today, when we're done here, you can be like, oh, there's more videos for me to practice with. So don't worry. A lot of people don't realize that there's practice videos, and that's why I show it. So thank you for asking, because I bet you someone else is like, I didn't know that either. So we are looking for the 75th percentile of reaction times on a curve with a mean of 150 and a standard deviation of 10. So far, all of these graphics look pretty accurate to me. So all of these graphics, as in have the right mean and have the right standard deviation. I'm kind of just bringing this over here to the right page so I can look at it all at one time. So all of these graphics have a mean of 150 and a standard deviation of 10. Does that make sense right here, Priya, that we see here the mean of 150 and a standard deviation of 10 on all these graphics? So they're all the correct mean and standard deviation. But now I need to find the 75th percentile. If you hear the 75th percentile, you would think that the 75th percentile, and that's the first thing we need to know, means that what? Let's do a drawing of it. Let's do a drawing. It means that what? The 75th percentile means on this curve that what for the curve? The 75th percentile means what for this curve? Like if I say 75th percentile, that means in context, for this curve what? The 75th percentile means what for this curve? Like, what would that mean for us? To say something is at the 75th percentile. Like, I'm in the 75th percentile of this. So that means what? What does that communicate to somebody? If I say 75th percentile, so you can see this line right here is where the 75th percentile is at. And then what does that idea of 75th percentile communicate to somebody? So then we're like, okay, I need to know what this communicates first. This is what I'm looking for. I'd love to see something that looks like this. So what does that mean? So 75% of the data is below it, correct? So what's the amount of data above it? So what would be the amount? Now we're not looking for that, but the 75th percentile means that, what percent of data is above it. If 75% of the data is below it, which means it's the 75th percentile, that's what percentile means, is this amount of data is below this observation. So someone who's in the 75th percentile, 75% of observations, people on this curve are below them. That means 25% is above them. And this drawing right here is the key to solving the problem, because you see something here that looks very similar. Do you see any graphic here that looks kind of similar to our drawing? I have to disappear. Do you see a graphic 1, 2, 3, or 4 that looks similar to our drawing? Now, not perfect, but does any of these look kind of similar-esque to our drawing? Do any of these graphics look kind of similar to our drawing up there? 1, 2, 3, or 4. Do any of them look kind of similar? And then we'd be like, maybe we could use that to solve it now. Do any of those graphics look kind of similar? Number 4, great job, Priya, right there, another 100 points. So let's go ahead and grab graphic number 4 right here. We're going to have to cut down this image, but we're going to take graphic 4 as our main sort of inspiration to solve this question. So let's think about how graphic 4 can help us solve this question about what is the 75th percentile. Now, graphic 4, and we'll see it here in a second, graphic 4 is not showing us the 75th percentile. Graphic 4 is showing us the what percentile. We'll zoom in so we can see it. Graphic 4 is not showing us the 75th percentile. Graphic 4 is showing us the what percentile. So it's not showing us the 75th percentile. And we can look at the percentile by the area shaded on the curve. It's showing us the what percentile. Graphic 4 is showing us the what percentile. And this value right here is where that spot is at right here. That's where that is at. It's showing us not the 75th percentile because it's saying below this point is 25% of the data. That's the 25th percentile. So Priya, if we could just magically take this curve right here, if you look at our images, what we have, what if we could just magically take this curve right here and just say, you know what I really want? I really just want the curve to look like this. I mean, wouldn't that just be great right there to say, I just I'd like it to be on the other side because then I would know that point, right? Does that make sense logically? Like, if we could just flip it around. Well, what do you think when it comes to the 75th percentile? The 75th percentile would have the same what from the mean. So here's where the 75th percentile is at, because the 25th and the 75th percentile, like there's where the 25th is at by virtue of the problem. And the 75th would be over here. They would have the same what from the mean. Same distance, right? Great answer. Now here's the easy way to solve this problem, and I go over it more exactly. This makes it really easy to figure out in your head. You ready? Let's pretend this is 143. I know this doesn't solve the exact problem. You would just do the mathematics and carry the decimals. But how much below the mean is that? So you just carry decimals. I'm just doing it as an easier solve because then it's like, because we have to understand what we're doing. It's not about solving math. It's about understanding what we're doing. So how much below the mean is 143 from 150? So we're just finding how far below the mean is that. So how far below the mean is 143 from 150? And if you want to do the exact one, just carry the decimals to find out the distance it is away. But 143 is how much below 150? And that's all we're thinking about right now. So how far is that from the mean? And so 143 from 150 has a distance of what? What is the distance 143? It's 7, right? So that means this has a distance of 7. And in our rounded version of the problem, what is the answer to this spot? where would that be at? And I drew it decently. So it's kind of close to it. But where would that be at now? If that has a distance of 7, that spot right there would mean the 75th percentile is where on the curve. So, and you can carry the decimals if you want. But boom, Priya, you got it right there. So it's a pretty tough problem. We can do question 4. This was 4, now we'll do 5. But that's a pretty tough problem right there. So, and if you carry the decimals, you would just take and subtract the difference from 150 minus 143 point. There's the distance right there, and then you would add that to 150. So that's the exact answer. Like if you carry the decimals. So we just kind of rounded it to make it make sense. But carrying the decimals would obtain this right here. Once again, subtracting the difference from 150 to find out how far it is away. And then adding that because there's a symmetry to the distances of the 25th and 75th percentile around the mean. But that's a really good problem. Really good one. And check out the other video if you want to see an additional solve on it. We're going to do one more segment. It is time for the last question of the day. So let's get that last question going. Question 5. Ooh, it's a big one. So we're going to have to solve it quick. Do a little bit of speed run on this. Z-scores and the normal curve. Really great stuff to know right here. So it's a great question, Priya. Remember those videos. Check them out if you need. Let me put a timestamp. I like doing review. So at 201, swing by. We got this. Practice for the test. Stat 201. Exam 1 review. Review question 5. And let's go check it out. Here we go. So I do want to say once again, if you're looking for another version of solving these problems, do check out review 1 page. Part 2, you bet. Here we'll do part 1 very, very quickly here. So you ready? We're going to speed run part 1. Calculate the z-score. So we should know the z-score formula. The z-score is going to be the observation minus the mean over the standard deviation. Observation minus mean of distribution over standard deviation equals to z-score. So we need to identify the observation has a mean of this. Is that the mean? And the standard deviation is this. And the observation is 2. So we're just going to plug in the numbers right there and do 2 minus 2.5 over 0.32. And this solves to a z-score. I hit the wrong button right there. This solves to a z-score of, it's below the mean. So that's 0.5 negative divided by 0.2. There we go. So that's the z-score. Negative 1.56. There we go. Negative 1.56. What percent of this brand can be expected to last 2 years or more under normal conditions? So what is our first thing we do when we see something like this, Priya, right here? What should we do? Great job, Priya, on the z-score right there. What should we do if we're asked to do like normal curve, empirical rule stuff? If you see this, what should you immediately be looking at? Which you can't bring to the test. Draw the curve, Priya, 100 points right there. Draw the curve. So what we have right here is the following. Here's our normal curve. And we're going to put right there, and that's a great answer. We're going to put right here the mean of 2.5, and I do it a little bit slower in the problem. And then we're going to go down standard deviations right here. And we're only going to draw what we need on this. We're only going to draw what we need. Down one standard deviation is 2.18, and a down another standard deviation is 1.86. And I'm going down by 0.32 each time. So 2.5 minus 0.32 is standard deviation, and there we go, confirms answers. We got it. Always below your curve, put the z-scores. We don't need to really solve any other numbers, but we already knew the z-score, so technically we didn't need the context. I always like drawing the context and the curve itself. So we're asking about an observation that landed right here. That's what we're talking about. We're talking about something with a z-score of negative 1.56. Now, if you were to guess this value, what percent would you just guess it to be? So just give me a guess. Does that look like 1% of the curve I'm shading, 2%, 100%, 50%? Just come up with some logical guesses because it says what percent are expected to last more than 2 days or hours or something. It says what percent are expected to last more than 2. So it wants to the right of 2. It says more than 2. So logically, what would you guess? Just a guess. More than 50%. Great job. Elizabeth Grannis right there. 80%. That's pretty close. Pretty good guess right there. So now we're going to narrow it down. Would you agree with me, though, that we would have something that is, here's our small arrow, and here's our large arrow. When we had questions like this on the test often, I'd always teach it this way by the small and large arrow method. So it must be an error, or must be an amount between what of those areas. Like if I say the small arrow is this amount, and the large arrow, I'm going to click down here. There we go. Now it shouldn't move it. The large arrow shows this amount. The amount of area shaded right now must be what to the small and large arrow. The large, or the arrows right here, the amount of area we've shaded must be must be what to this. I'm not trying not to say it. I want you to think of it. So the amount we've shaded right here must be what to these arrows. Like if we say from here over on the curve, that's what the small arrow represents. Or from here over on the curve, the amount of area shaded here must be what to these values. Well, to the large, it's going to be less than this, right? Because that's too much. And then to the small, it's going to be more than that because that's too little. Like if you shade from here over, that's not enough. So the amount of area is going to be what to these arrows? It's going to be between, right? So it's going to be between these values. So the question becomes, how much is over from those arrows? So this is where knowing the numbers is a huge help. Let's remove out the context and just use the z-scores for now. Between -1 and 1 is 68% of the curve. What is outside of -1 and 1? So what is outside of -1 and 1? So we're doing the first arrow right here. What is total outside of it? And that's going to help us find this arrow right here. So what is total outside of -1 and 1? 68% inside. So total outside would be what? It would be 32, right? And that leaves 16 on either side right here. Great job, Priya, right there. Great work. It'd be 16%. So Priya, how much is this arrow worth right here? How much does this arrow cover on the curve? So look up here and just think about just the arrow, which is from here over. How much area does that cover on the curve? I hate that it does that when I work on questions sometimes. I try to delete with it and it does that. How much is this area on the curve right here? How much is that? Gotta go in just a moment. That is going to be how much area on the curve? It's going to be 84. Great job, Priya. Excellent work. And then we need to figure out the second arrow. We're going to lose the shading right here. Whoa, no, we can't lose the normal curve. We can't lose the normal curve. We need that to solve it. Oh, there we go. Perfect. Now, the second arrow is going to be contained within here to here, and that's 95. And so outside of 95 is 5%, 2.5 on either side. So the second arrow, which is the too big arrow, is going to have across these values, because this is too much right here. And the too much arrow has 97.5. And these are our two answers that area right there must be between these values. So it's something smaller than 97.5, but needs to be bigger than 84. Have you gone over? Yep. Check out the office hours on Friday. Let me drop that in the chat right there, Elizabeth. Might still have a quick way to get to it right here. 2 seconds right here, and I'll drop this in the chat for you. But Priya, does that make sense right here, there on that one? Let me go here to Stat 201, videos, the office hours pivot help right here. And so Elizabeth right there, there's pivot help. And I'm teaching in 10 minutes. Gonna go eat some lunch right here. There's the pivot help. Check it out. Puppet Shark, great office hours. Email me if you got questions. We'll be back here soon. Did he appear? Puppet Shark. Thank you, Puppet Shark. Bye for now, everyone. Bye. Class in 10 minutes. Not 201, though.